So we want to now introduce several very famous differential equations. These differential equations arise in science and engineering applications and have names associated with them, names of scientists and mathematicians who invented them and so on, and they have been found later on in many other contexts. So we call these special ordinary differential equations. They all have variable coefficients in them. So the first of these is the Bessel's equation, or Bessel's differential equation, which is written over here: x squared y double prime plus xy prime plus x squared minus nu square is a factor multiplying y equal to 0. So this second order differential equation has a parameter nu showing up in the coefficient here, and that is called the order. So solution to this differential equation, the two linearly independent solutions are called the Bessel functions, and they are denoted with a label J, a symbol J, capital J. And so the general solution is written in this form: C1, an arbitrary constant, times J subscript nu of argument x, independent variable x, and this is the second linearly independent Bessel function. We will define Bessel functions more formally and so on using series solution as well later on. Let's make a note of some fundamental properties of Bessel functions. We can think of Bessel functions as cousins. They are related to sine and cosine functions. They give solutions which are oscillatory in space as sine and cosine functions are. And so, for example, if we were to plot J0 function as a function of x, we can note that J0 starts with a value 1 when x is equal to 0, and it oscillates around x equal to 0 and crosses the x-axis at these points where the red circles are marked. And the amplitude of this oscillation decays as x becomes large. So unlike sine and cosine functions, which continue to oscillate at constant amplitude, Bessel functions have a decaying amplitude as you go to large x. They are richer than sine and cosine functions, and they are cousins of sine and cosine in the sense that in problems where sine and cosine functions appear in a planar geometry or in rectangular geometry, if we consider circular geometry or spherical geometry, then the related functions that show up are Bessel functions and so on. So we can think of them in that way. Another differential equation which is related to Bessel's equation is the so-called Airy equation. Airy was a very famous mathematician, astronomer, and did a lot of work on many problems, including optics and wave propagation. And so the differential equation that is named after Airy is a very simple equation written here: y double prime minus x times y equal to 0. And if we want to get some intuition about the behavior of solutions to this equation, pretend that we think that x is some constant. It's not a constant. X is the independent variable. It's going to vary. But just to get some intuitive feel for what the behavior is going to look like, if we freeze the value of x, then depending on whether x is positive or negative, we can see that this differential equation locally and around that point is something we are familiar with. So if x is a negative number, then this will be overall a positive constant here. Minus x will be a positive constant. And so y double prime plus some positive number times y equal to 0 is a differential equation for oscillations, sine and cosine solutions that we have encountered before. And if this constant is a negative constant, which would be the case if x were positive, then that is an equation which has exponential solutions, growing and decaying exponential solutions. So this simple equation actually is called an equation with a turning point. It in fact provides solutions that are oscillatory for negative x, and they are exponential solutions for positive x. It combines oscillatory solutions with exponential solutions in a single equation. And so that turning point where the nature of the solution changes from oscillatory nature to exponential nature is at x equal to 0, and that is called a turning point. And this is the simplest equation with the turning point, and often solutions to Airy equation can be used to model or approximate a more complex behavior of turning points that arise in applications. So finally, let's consider another famous equation called Legendre differential equation, which is noted here. And this has a multiplying factor for y double prime is 1 minus x squared. So this coefficient would vanish when x is equal to plus and minus 1. And so this equation has singular points at x equals plus and minus 1, whereas the Bessel's equation has a singular point at x equal to 0. And the rest of the coefficients over here. And this equation has solutions in terms of polynomials, which are called Legendre polynomials, that we're going to be discussing later on. And so there are many other very celebrated equations. At this point, I should note that make use of many resources that are available on mathematical functions, special functions in Mathematica or in Maple or in mathematics handbooks. These functions are and their properties are listed, and how they are used is also illustrated. So there are many resources that you can use to learn about special functions that arise in applications. Okay, moving on now. We want to note that all of these cases are in fact, and many others, are special cases of a differential equation which is called the Sturm-Liouville differential equation, abbreviated here as SL later on. And that equation can be written in this form, where we have this second derivative term rewritten with function px inside here, d dx of p times dy dx, in curly brackets, denoting that d dx of this whole product is to be taken, minus q times y plus lambda, which is a parameter, times another function r of x times y equals 0. Note that both of these terms depend on y. The term which depends on the first derivative of y has been combined with the term involving second derivative, and all of that has been put inside here. And this is something that is always possible to do. And so let's say that the equation is defined over an interval where x is varying between 0 and 1, and that is the interval I that we are going to be using. Of course, if the range or the domain of x is different, we can rescale x so that it becomes this range, and so that way we can deal with more other problems as well. So we note that this equation is a homogeneous differential equation. And so along with this differential equation, we have boundary conditions. And so the boundary conditions are stated in this form. The value of the function as 0 and its slope, a linear combination of them with constants a1 and a2 is equal to 0. And likewise, at position 1, at x equal to 1, the linear combination of the solution and its derivative with constants b1 and b2 is set equal to 0. Of course, these are known constants, and there may be situations where one of these, a1 may be 0 or a2 may be 0, b1 may be 0 or b2 may be 0, but it is assumed that a1 and a2 are not together 0. So one of them is at least non-zero, or they could both be non-zero. That's both are possible. And so these boundary conditions are, in particular, are, you can note that some quantity that depends on the dependent variable, which is a linear function of the dependent variable, is set equal to 0. So these are homogeneous boundary conditions. So we have a homogeneous differential equation. We have 0 on the right hand side, and we have 0 on the right hand side for boundary conditions. So together they define a homogeneous boundary value problem. This is a boundary value problem as opposed to initial value problem, because we have two conditions that are posed at two different values of x. If both conditions were posed at the same point, then we call that initial value problem, as we had discussed before. So this is a homogeneous boundary value problem. In fact, this problem associated with the Sturm-Liouville equation is called the Sturm-Liouville boundary value problem, and we will see that this indeed is an eigenvalue problem. It's an eigenvalue problem in the sense that this problem does not have solutions for arbitrary values of lambda. There are particular values or characteristic values or eigenvalues corresponding to particular values of lambda. Only for those particular values of lambda can this equation be solved. If we think back as to the context from which such equations arise, these values, lambdas that show up, have physical interpretation, many times as associated with frequencies, natural frequencies of oscillation, or some particular behavior which can be physically interpreted. For example, in quantum mechanics, lambdas would be eigenvalues associated with the Schrodinger equation that one may be dealing with. So there is a result we want to summarize here, and then we will extend this discussion in terms of stating properties of solutions to the Sturm-Liouville boundary value problem. The result we want to state is that over this interval I, if the coefficients that are involved here, p, the first derivative of p, and q are continuous functions over this interval, and the factor r, which is called a weight function, we will see later why it's called a weight function, that this weight function is a positive number. It can vary, it's not a constant, but it needs to be positive over this interval. Then one can rigorously show that the Sturm-Liouville eigenvalue problem has a discrete infinite sequence of eigenvalues. We can denote those eigenvalues as lambda equals lambda j. There is a sequence of such eigenvalues and the corresponding eigenfunctions y of phi j, which solve the original homogeneous differential equation with the boundary conditions. And so this set of eigenvalues and eigenfunctions become extremely useful in solving a variety of problems, as we will illustrate.